Welcome to the chromatographic process. So recall increasing the rate of equilibration of a solute between the stationary phase and the mobile phase increases the efficiency of our column. That is, it decreases the plate height h, thereby increasing the number of theoretical plates on the column n. In capillary gas chromatography, the equilibration time can be decreased by using a narrower column. Narrowing the column decreases the distance between the center of the column and the stationary phase on the wall, thereby decreasing the time required to diffuse from the center of the column to the stationary phase. Now, because diffusion in liquids is around 100 times slower than in gases, open tubular columns are impractical in liquid chromatography. That is, the diameter of the liquid channel would be too large for a solute to diffuse through in a reasonable time frame. Instead, liquid chromatography uses packed columns. In a packed column, the solute doesn't have to diffuse far to reach the stationary phase. With a packed column, efficiency increases as the particle size decreases. And with HPLC, the particle sizes are typically 1.7 to 5 microns. So, in this figure here, we have 3 chromatograms, A, B, and C. A uses 4 micron particles and has 2,000 theoretical plates. B here uses 1.7 micron particles and has 7,500 theoretical plates. C uses 1.7 micron particles but uses a stronger solvent to decrease the analysis time. That is, we're lowering the retention factor of our solutes on the column in that stationary phase. So here are some Van Demeter plots of plate height versus the linear flow rate for various particle sizes. We've got 5 micron here, 3.5 microns there. We have 1.8 microns here, or 2.7 micron fused core, superficially porous. So they're solid on the inside, but they're porous on the outside of those particles. So note that as the particle size decreases, the plate height decreases. And remember that as plate height decreases, the number of plates increases, thus increasing the column efficiency. So we want to be low on this axis. However, as particle size decreases, the plate height becomes less dependent upon the flow rate, because now this higher flow rate side of our minimum value gets shallower and shallower at lower particle sizes. That is, with small particles we can decrease the analysis time with little decrease in the efficiency. At the optimum flow rate for each column, the number of theoretical plates is approximately 3,000 times L, the length of the column, divided by dP, and dP is the particle diameter in microns. Note that the length of the column is in centimeters. So one reason why small particles provide better resolution is that they reduce the multiple path term, the A term, in the Van Demeter equation. That is, they provide more uniform flow paths than do larger particles. So remember that A term is a flat line here, and so as we get higher particles, the whole curve has been moved up. As we get lower particles, the whole curve is moving down. Additionally, the distance through which the solute must diffuse to reach the stationary phase is on the order of particle size. And thus, the smaller the particles, the narrower the solvent channels between the particles, and the faster the solute can diffuse from the center of the solvent channel to the stationary phase. That is, that C term in the Van Demeter equation also decreases as we lower particle size. Furthermore, with smaller particle sizes and higher flow rate, the analyte is not diluted as much as it travels down the column, and that means that the detection limit is lower. Now, there is a penalty to using smaller particles. Increased pressure to push the solvent through the column, because as those channels between the particles get smaller, we're going to have to push the solvent harder in order to force it through those narrower channels. So the pressure required to push the solvent through the column is given here, where Ux is the linear flow rate. This eta term, that's not an N, that's an eta, is the viscosity of our solvent. L is the length of the column. R there is the column radius, dp is the particle diameter, and this term over here, this F, is a factor that depends upon the particle shape and the particle packing. So note that the pressure is directly proportional to the flow rate, U sub x here, and the column length, L, and it's inversely proportional to the square of the column radius, it's inversely proportional to r squared, and the square of the particle size, so dp squared. And therefore, in moving from the 4.0 micron particles and 4.6 millimeter diameter column in A to the 1.7 micron particles and 2.1 millimeter diameter column used in B, the required pressure increases by a factor of 27. So commercial HPLC instruments can operate at pressures up to 100 megapascals. This is 1,000 bar or 15,000 pounds per square inch PSI. And this allows us to use small particle sizes to increase the resolution and or decrease the analysis time. Now, there is a second penalty to using smaller particles, and that is increased frictional heating. As the solvent is forced through those fine particles in the column, the friction causes it to heat up. That is, the center of the column is warmer than the outer wall, and the column outlet is going to be warmer than the column inlet. So a 100 millimeter long column with a diameter of 2.1 millimeters that contains 1.7 micron particles generates a temperature difference of around 10 degrees C between the inlet and outlet when the solvent is acetonitrile. The temperature difference between the center of the column and the column wall can be around 2 degrees Celsius. So temperature differences within the column can contribute to band broadening and thus should be minimized. Now, chromatography columns are expensive and can easily be degraded by dust or particles in the sample or solvent and by irreversible adsorption of impurities in the sample or the solvent. The samples should be centrifuged and or filtered to remove the particulates. The columns used in HPLC are generally made of steel or plastic. They're 5 to 30 centimeters long, and they have inner diameters of 1 to 5 millimeters. Typically, a guard column is used, which contains the same stationary phase as the main column. So fine particles and strongly adsorbed solutes are retained in the guard column. The guard column is periodically replaced when the column pressure increases or after a set number of injections or a set time. The chromatography column is heated to lower the solvent viscosity, which reduces the required pressure or increases the possible flow rate. The increased temperature will also reduce the retention time. However, the increased temperature can cause degradation of our stationary phase, which decreases the column lifetime. If the column is not heated, its temperature will fluctuate with room temperature, and thus heating the column 10 degrees higher than room temperature will improve the reproducibility of retention times and the precision of quantitative analysis. So, the most common support for the stationary phase is high-purity, spherical, microporous particles of silica, and these particles are permeable to the solvent and have very high surface area, so this is a few hundred square meters per gram. Note that silica dissolves in base and thus cannot be used above pH of 8. For adsorption chromatography, the bare silica surface can be used. For liquid-liquid partition chromatography, the silica surface is coated with a liquid stationary phase. The stationary phase is covalently bonded to that silica surface via reactions with the silanol groups. So we have our silanol group here, and we react our liquid stationary phase with it, and now we have a covalently bonded stationary phase there, and we get a similar sort of thing down here. So common polar phases are amino, where we have the amino group at the end, cyano groups, and diols. Common nonpolar phases are the octadecyl, the octyl, phenyl, and the F5 phenyl, so the fluorinated phenyl group there. And by far the most common stationary phase is that octadecyl stationary phase, this one here, which is abbreviated ODS or C18. Another type of nonpolar stationary phase has a polar embedded group. That is, near the base of the hydrocarbon chain, a polar group is bonded, for example, an amide. Such stationary phases allow different selectivities from our C18, our octadecal stationary phase. They also allow the mobile phase to be 100% aqueous, whereas other nonpolar stationary phases should not be exposed to 100% aqueous mobile phase, or they will become very difficult to re-equilibrate with a nonpolar solvent. So in adsorption chromatography, solvent and solute molecules compete for sites on the stationary phase. So here we have some solute particles, those are these blue triangles, stuck on our stationary phase. As the solvent flows past, some of those particles, some of those solute molecules get removed via competitive adsorption by the solvent. And that means that elution is occurring when the solvent displaces our solute from that stationary phase. Now, different solvents have different relative abilities to elute a given solute from the adsorbent. These relative abilities to elute solute are nearly independent of the nature of the solute. So, an allotropic series ranks solvents by their relative abilities to displace solutes from a given adsorbent. The eluent strength, symbolized here with an epsilon naught, is a measure of the solvent adsorption energy. The value for pentane on bare silica is defined to be 0. The more polar the solvent, the larger its eluent strength for adsorption chromatography on bare silica. The larger the eluent strength, the faster the solutes will be eluted from the column. In normal phase chromatography, the stationary phase is more polar and the mobile phase is less polar. In this case, a more polar solvent has a higher eluent strength. On the other hand, in reversed phase chromatography, there should be a space here, the stationary phase is less polar and the mobile phase is more polar. And in this case, a less polar solvent has a higher eluent strength. Generally, the eluent strength is increased by making the mobile phase more like the stationary phase. And that brings us to isocratic and gradient elution. In isocratic elution, we're performing the chromatography with a constant solvent mixture. And this may be a single solvent, or it may be a mixture of two components in a fixed ratio. On the other hand, gradient elution is performed with a controlled variation in the composition of our solvent mixture that we use. Gradient elution is useful when one solvent does not provide sufficiently rapid elution of all of our solutes. Recall that a hydrophilic substance is soluble in water and or attracts water molecules to its surface. So polar organic molecules have hydrophobic regions to them. Hydrophilic interaction chromatography, or HILIC, is useful for separating small polar molecules that have low retention times on reversed phase columns. And the stationary phase is highly polar, and we've got a few examples over here. The mobile phase is a highly polar organic solvent, often acetonitrile, mixed with aqueous buffer. The solutes then equilibrate between the mobile phase and a layer of aqueous phase, so water, on the surface of the stationary phase. The eluent strength is then increased by increasing the water content of our mobile phase. That is, the gradient dilution goes from low water content to high water content. So figure 2415 shows a decision tree for choosing how to separate the components of a given mixture. The top half here is for analyte mass below 2000, and the bottom is for analyte mass above 2000. And here we've zoomed in just on the top. That first branch, so whether we're going this way or that way, is for whether the solutes are soluble in organic solvents over here or water over there. And then further branches, so this branch here or this branch there, depend upon the earlier paths taken, but generally involve the polarity of the solutes. So that's this branch here and that branch there. So now let's talk about solvents. To prevent column degradation and minimize background signal in the detector, high purity, so HPLC grade, solvents have to be used. And such a high purity is expensive. The solvent must be filtered to remove any particles larger than 0.5 microns. So the solvent also has to be purged with helium or evacuated in order to remove dissolved air. These air bubbles, if we leave them in, will create problems with the pumps, the columns, and the detectors. Dissolved oxygen will degrade the column, and it absorbs in the 200 to 250 nanometer range, thereby interfering with an ultraviolet detector. After a reversed phase separation, the column should be washed with 10 to 20 mobile phase volumes of a strong solvent to dissolve any strongly retained solutes. A normal phase separation is sensitive to water in the solvent, and to speed equilibration between the stationary phase and the mobile phase upon changing eluents, the organic solvent should be 50% saturated with water. Now, a volume of water-saturated solvent should be mixed with an equal volume of dry solvent to give us that 50% saturated solvent. The solvent can be saturated with water by stirring with a few milliliters of water, followed by removal of that excess water. After a gradient dilution is used, 10 to 20 mobile phase volumes of the starting solvent mixture should be passed through the column to equilibrate for the next run. And this volume can be reduced to around 3 mobile phase volumes if the solvent always contains 3% by volume of 1 propanol. Now, that propanol is believed to coat the stationary phase with a monolayer of alcohol. And if the propanol concentration in the solvent is constant, so always at 3%, then that monolayer doesn't change much over the run. And this means that the mobile phase environment that the stationary phase sees doesn't actually change that much over the run, and real equilibration time is minimized. And that was the chromatographic process.